Hello, I'm Adam Rutherford and this is the Kavli Prize for 2016. It's my privilege to talk to the three winners here today of the Kavli Prize for Nanoscience, in the words of Fred Kavli, the very, very small. Gert Binnig, Christoph Gerber and Calvin Quate are the minds behind a new way of looking at the atomically small and also to sculpt effectively with individual atoms. The invention of atomic force microscopy has revolutionized our ability to see at the ultra-fine scale. So I want to start by asking Calvin Quate how this idea came about in the first place.
I was traveling to London when I read an article by Herr Binnig, and I diverted and went to Zurich. When I saw the work that was going on in Zurich at the IBM Research Lab, I knew my program at Stanford had to change. So I changed everything at Stanford, put 3 students on this project, and the result is today, I guess, the AFM.
It was as immediate as that, was it? You knew instantly that you had to change?
Yes, I do.
What was it about what you read that made you instantly change?
The fact that he was scanning a tip over a conducting surface and he could move atoms, which was to me amazing. And I knew I could build a similar structure on a cantilever and look at both insulators and metals. And I succeeded in doing that at Stanford.
So, Gerd, how did this work for you? All of a sudden you had a phone call and Calvin Quate turned up at your lab and said, we need to work together.
Yeah, actually I was not there at that time. So Christoph talked then to Cal.
And what were you surprised at this
Well,
someone turning up unannounced?
Well, obviously, because I mean, the work was published, and Cal knew about that then when he read the story, and so he came by and was just so interested in what we were doing, and I showed him in the lab the way we were doing it. That was the predecessor. I mean, we're talking here about the STM, the scanning tunneling microscope. And so I just explained it to him, you know, what we are doing. And he was fascinated by that.
How did the collaboration work?
The collaboration, I think, worked very well because they were willing to share their ideas. And I invited Herr Binnig to come to Stanford for a year, hoping to get the result of his brilliant ideas. As it turned out, he found the Stanford golf course. During the day, he was on the golf course. So that is the way that worked out, but I enjoyed the collide.
Is that true, the charge of playing golf instead of inventing the future?
No, I played golf during the day and I worked during the night.
Okay,
So
that's fair enough. So this was in the early 80s, mid-80s?
Yeah, 85.
And working on a slightly different technique which would become atomic force microscopy.
That's correct.
But how many iterations are you going through in inventing this tool?
Yeah, not so many. I mean, we were looking for how to investigate also insulated and biological material, which we couldn't at that time. And then suddenly we had the idea maybe forces could make it. Yeah. Before we measured everything with a current, but a current you can't guide through an insulator, yeah? Wouldn't carry the current. So forces might be possible, but then we had to think, can you actually measure the forces between 2 single atoms? If you want to have atomic resolution, you need to feel the atoms and measure those forces.
Okay, so maybe you could describe the tool itself, because I'm a mere biologist, so it's all a bit abstract to me, but what is it actually doing? I've heard you talk about it as a bit like a a stylus on a record player.
Yeah, that's perfectly true. It's a very good comparison. So you, like in the stylus, you use a tip, or like in the old record players, you use a tip, bring it very close to the surface, and the tip hopefully ends with a single atom. And then you have your atomic structure on the surface, and this tip should then sense the attractive force between this front end of the tip and the atoms on the surface. And if you feel this, you can scan over it and feel the contours of the atomic structure.
I mean, that's an astonishing level of resolution that this needle is tracking over, well, not the grooves of some music, but is it actually measuring the interactions of individual atoms?
That's absolutely true, yeah.
Absolutely.
But that's breathtaking. I mean, you say it so casually, but to me, used to light microscopes,
Yeah.
that's millions of times.
Yeah. It's about 1 million times better than a record player, actually. And then you get atomic interaction.
The remarkable thing about the work in Zurich is they could move single atoms, manipulate single atoms, which I found quite remarkable.
Well, that is the second remarkable thing, which I think is probably even more impressive, is not just tracking over the surface, but the ability to deposit single atoms.
Yeah.
Well, how does that work?
Well, there's a certain force between the tip and the atoms, and as you move the tip, the atoms would follow because there was an attractive force. And I think, and the tip was sharp enough to focus on a single atom.
And how do you know that you've deposited a single atom on a surface? How can you control and then subsequently measure that there's one there?
Yeah, that's right. But you have this microscope. You always can do something to the surface, change the position of an atom, and after that you look what you have done by just imaging the surface that you modified.
And then you see it where you displace it, on the surface. And so you can start manipulating, picking up other atoms and then move it there if you want to. Basically sculpting a structure, a nanostructure. That's how you do it.
You make it sound like Lego. You just pick up a brick and put one there.
Yeah.
And
Yeah.
is it as easy as that now with this tool, with AFM?
Yeah, today it's very easy. You have algorithm that you can sort of do that, and then it does it basically automatically.
And you mentioned it earlier, but this, again, for a biologist, this is really significant as a technique, because being able to look at wet material and being able to look at living tissue at this resolution is totally unprecedented. What is it about AFM that allows you to look at cells?
Well, it's in that case, it's you have to have a very, very sensitive cantilever in order, and then you do it in a dynamic way. You operate it at this resonance frequency, and in the fluidic, the quality factor of it goes down basically to nothing, and you hardly touch actually the molecules, and with that, it is possible to image surfaces and molecules on a molecular layer, and that's the trick behind it in imaging molecules.
I don't think that biologists mostly think about their biomolecules at an atomic level. In general, we think about cells and proteins and sometimes individual molecules. But what can knowing the atomic structure of a living molecule, how can that inform biology?
Yeah, there was some very early some interesting measurements from Andreas Engel in Basel. They measured ion channels, which you have on the surface of a cell, letting ions in or out, and he could actually measure them at work. So channels opening or closing, and you could see it. He can control this. So this is something biology is always imagined, but now you can look at it and see it, how it works.
And also, crucially, in living tissue. So we've had electron microscopy for decades, but that can only be done on
absolutely
tissue that's
in fluidic environment. You can do that.
It's astonishing. Were you surprised, all of you, at how AFM caught on? I mean, it's used everywhere in so many different fields now. Was that a surprise?
So many inventions, actually. Not only our invention was there, but also many inventions followed. So imaging in liquid, in water, was an invention that came a little later. And also to operate with a laser, for instance, which is suitable to measure those biomolecules in water. That also was an invention that came a little later. So
I would say there are many things in the nano world that come as a surprise to me. He opened up a whole new realm of investigation.
Were you surprised that it had so many applications?
I was surprised that you could move the atom. That, I think, is the thing that sticks in my mind.
And of the applications, what do you think have been the most significant? The Kavli Prizes are celebrating basic research, but this is a tool, isn't it?
Absolutely, it's a tool. And coming back, the question before, what Gerd said about design channels. Now, the development of high-speed AFM, where you actually can image, monitor those reaction, this biochemical reaction. You can now image that in real time. So that was a development, for example, of another AFM that took those people in Japan 15 years to develop a high-speed AFM. You just see sort of what it takes to do that. And for us, it was obviously a big surprise that you could do that, that you can do that now in real time. That you can image biological action in real time.
So let's leave aside my own biological prejudice here, because I am a biologist. But outside of biology, what would have been the really significant? I know there are many techniques now, there are many different AFMs and how it's applied, but what have been the really big ones that have had a major impact?
You mean in terms of instrument? Or?
Yeah.
Yeah, there are several methods around. Some of them, they operate a little bit like a record player, where the tip is in contact with the surface. This is such a nice simple instrument where you image with very high resolution, extremely fast and nicely, and you can do it operate it in your daily work, and it's no problem at all. That's used by many people. It's widespread. And then there's the other technique where people try to measure really single atoms in ultra-high vacuum, for instance, where everything is under control and you know exactly what you are doing, and you can actually also move then the atoms around and can do chemistry right on the spot. You change maybe a molecule by applying a little bit of a force, or you apply an electric field, and the chemistry changes just from a single molecule, and you can switch it back and forth, play all these kind of games, and I mean, this opens a completely new chemistry world. So that's something very different from the other applications. And then there's also biology really in play. So in biology, I would say to bind or not bind is the basic question in biology. All the interactions between cells is through binding. And now you can measure those binding forces between individuals, molecules. You just let them bind, and then you pull it apart by the tip and the microscope, and you measure the force, how strong was the binding. And then you know a lot about the biology that's going on.
And then, of course, there's the imaging, the fact that it's a microscope. I remember, I think it was in 2009 when the sort of proof of concept, I think it was pentacene, was it? The famous paper.
Yeah, yeah.
Which
That is 2000 and it was 2009. Yeah, that's right.
But it was a very striking image. It really was the first time we'd seen a molecule in its atomic
what you
shape.
do, what those people done, that came out of the IBM lab actually in Zurich, and what they've done is they picked up a CO molecule on the tip, and with that it was possible actually to address the chemical forces, and with that you could image a pentacene molecule molecular resolved. You know.
Well, it was like, it felt significant to me when that happened, because for years we draw at school and you know, we draw ball and stick diagrams.
Yeah,
this is what an atom looks like.
Yeah.
And it turns out that that is what an atom looks like.
Yeah, that's true.
Because we could actually see it.
Yeah, and actually they have sometimes then they have a chemical reaction and you don't know exactly what came out of it, and now you just look at it, and you see exactly what kind of molecules you produced through your process. Yeah.
And you resolved the chemical bonds of the molecule.
Them.
You see it, you know. So you can correlate the length of the bonds in the molecules and so on.
Yeah.
So that is the technique what I just explained before, you know, with that CO molecule on the tip. That brings this unprecedented resolution.
So it has revolutionized so many different fields, and it's been applied across so many areas of the sciences. I suppose my final question is, well, what happens next? Where do you go from here? what would you like to invent next?
If you tell us, we'll win another prize.
Give us some hints. Yeah.
But can AFM be developed any further? Is it refinement now, or is there a next big goal?
Well, from the way I see it, you know, I mean, what have been done just in recent years is absolutely fabulous. The way people have picked on this and developed, coming back to the high-speed AFM, which took 15 years to develop, you know. So I'm personally sure that people will take it to the next stage.
Higher resolution? Quicker?
Yeah. No, for me, actually, there are two themes that are very important for the future. One is to build a nanoprocessor that you really process more, maybe on the molecular level, but a complex structure. We now know how to build those extremely fine structures, how to copy them, that you have many of them in an industrial reproduction. That's a different story. We have to learn that. And AFM can help here to do this. And in biology, I think we also need to go more in direction of complexity. We need to learn how we can treat patients with more complex interactions of molecules. And the interaction of molecules is something we can measure with the AFM. So if you have a complex treatment, not just with one drug, but with a network of drugs, would be the future, in my opinion. And there you need to learn how those molecules interact with each other.
Well, get your skates on, because we can't wait around for another 15 years for this. I'm joking, of course. Let me just, again, congratulate you. It is demonstrably a world-changing idea that you've built. So congratulations, Calvin Quate, Christoph Gerber, and Gerd Bennig.
Thank you.
Thank you.